This is Sami Janin of the EPFL. Welcome to our MOOC on basic steps in magnetic resonance. Today we shall be talking about dynamic nuclear polarization, and this is going to be the second part of this chapter. Today we shall be talking about the electron spin system and the nuclear spin system, that are the two key players in our DNP experiment. So what about the electron spin system? Let's take our nitroxide molecule that has a free radical sitting on the NO bond. Let's first assume that this nitroxide molecule is distributed in a matrix and that all these nitroxide molecules have exactly the same orientation. Well, in this case, one might observe a very narrow ESR line because all the electron spins will have the same frequency. Well, in reality, the frequency of the electron spins strongly depend on the orientation of the molecule with respect to the field, B0. So that in a real experiment where all the molecules are distributed randomly in the matrix such as a glass, the ESR spectrum is not anymore a narrow line, but a broad line. And each of this frequency here correspond to a certain orientation of the molecule with respect to the field. There is another mechanism that broadens the line, that is the hyperfine coupling. In this particular example, in this nitroxide molecule, there is a coupling between the electron here and the nitrogen that has a spin 1, and this coupling gives rise to a splitting that you can observe here on this spectrum. These two broadening mechanisms are usually called inhomogeneous broadening. There is another broadening mechanism that we call dipolar, and that depends on the coupling between electrons from one molecule and the other molecule. This broadening mechanism is usually called homogeneous. So most of the broadening is due to the inhomogeneous broadening in our case. So is due to the Zeeman interaction and the hyperfine interaction. And for this nitroxide molecule, the broadening is typically on the order of hundreds of megahertz per Tesla. So say you have an inhomogeneously broadened ESR line. So instead of having very well defined energy levels with populations sitting on one level here and one level here, in reality you have a distribution of energy level that is quasi-continuous. And the population distribution amongst this energy level is of course described by the Boltzmann law. Now, what happens if you shine microwave on one of these transitions? Well, we're going to see that what might happen is that you're going to dig a hole in the ESR line. So you're going to saturate the electron spin at well-defined frequencies. Now, looking back at our energy levels and population distribution, what happens is that by shining microwave at a specific transition frequency, for example here, you're going to tend to equilibrate the distribution of population among those two energy levels here. And that's what digging a hole means. Now I told you that there was a third broadening mechanism that was also very important, and that is called the homogeneous broadening. The width of the homogeneous broadening depends on the strength of the dipolar coupling between the electron spins, which grows with 1 over r to the power 3, r being the distance between the electron spins. And it turns out that this broadening is usually much weaker than the homogeneous broadening in the case of nitroxide radical. It is about 0.2 megahertz per millimolar of radicals. So if you increase the concentration of radical, you're going to decrease the distance between the electron spins, and this is going to increase the width of the homogeneous broadening. what is the consequence on the saturation behavior of the ESR line? Well, now, when you are going to shine microwave at a specific transition, you're going to hit a specific electron spin that has the right frequency and the right orientation. But thanks to the dipolar coupling, this saturation may be transferred to other electron spins by spin diffusion. So what happens is that when you shine microwave at a specific frequency, this perturbation actually might propagate across the ESR line by what we call spectral spin diffusion. There is another very important phenomenon that happens at the same time, and that is the T1 relaxation. So at the same time you try to saturate your ESR line with microwave and you try to equilibrate the population amongst the energy level, and at the same time this perturbation tends to travel across the EPR line by spectral spin diffusion, the T1 relaxation tend to bring back the population towards the Boltzmann distribution. So the saturation of the ESR line, which is a crucial step in DNP, is a competition between saturation, spectral spin diffusion that propagates the perturbation across the line, and T1 relaxation that tends to bring back the distribution of population towards the Boltzmann distribution. Now let's talk about the nuclear spin system. So we have discussed the presence of free radicals molecule in the sample, but these free radicals that are usually present at a millimolar concentration are surrounded by molecules that contains nuclear spins, for example, proton spins. In our example, we chose to talk about the pyruvate molecule that contains methyl group here with 3 protons. So the first important feature in this nuclear spin system is that the polarization will possibly redistribute amongst those spins by nuclear spin diffusion. So in a sense, all these molecules in the solid state at low temperature might talk to each other, and the polarization might be transferred from one molecule to the other. To give a pictorial idea of what spin diffusion does, let's take just a line of spins. So we have a line here of molecules, and we just assume that at a certain time some molecules have their spin polarized down, and some molecules have their spins polarized up. So that when we look at the polarization of the proton spins along this line, we see a big step function here, with a negative polarization here and a positive polarization here. So what spin diffusion is going to do is that it's going to redistribute the polarization in such a way that the polarization is homogeneous on a microscopic scale. Now, if by any means you manage to polarize molecules on this side of the line with microwaves and with DNP, what spin diffusion is going to do is it's going to propagate this polarization through the line in such a way that you might end up with almost all the spins polarized through space. This spin diffusion process is characterized by a diffusion constant, and in a static solid at low temperature, this diffusion constant is about 10 to the 5 angstrom per second, so that the length that the polarization can travel is proportional to the square root of d times the time. That means that if you wait about a second, your nuclear spin diffusion might lead you to the transportation of your polarization over typically tens of nanometers. Now in a typical DNP sample, the average electron-electron distance is typically on the order of few nanometers when you have about tens of millimolar concentration. So it is important here to realize that the nuclear spin diffusion is going to propagate the polarization on a scale which is already larger than the electron-electron distance within only a second. So now let's take our line of nuclear spins in our pyruvate molecule and let's add an electron spin here, a nitroxide. So what we said before is that the nuclear spin diffusion might transport the polarization spatially from one molecule to the other. Now let's see how this is working. Let's assume here we have a spin with a high polarization and here a spin with a low polarization, and let's assume that you have a dipolar coupling between those two spins that is going to be enabling spin diffusion. Well, as you can see, the spin diffusion is going to drive transition between this energy level and this energy level, which is an energy conservative transition, and will tend to equilibrate the population amongst those two energy levels. But now if we get closer to the electron, what might happen is that the coupling between the electron and the nuclear spin is going to shift the transition energy of the nuclear spin via the dipolar coupling. And in this condition, if we consider the coupling between this nuclear spin and this nuclear spin, we see that the zero quantum transition is no more an energy conservative transition. So in a sense, the polarization cannot flow anymore from one molecule to the other because of the effect of the electron spin on the energy transition of these nuclear spins. So what we usually say is that there is a region of space around the electron spin where the diffusion is stopped. The spins that are inside this space are said to be quenched or bleached because their frequency are shifted away from the usual NMR frequency. And the limit between this area of space and the bulk area of space is usually called the diffusion barrier. And this diffusion barrier usually has a radius of about half a nanometer. So in our sample, you have electron spins. Around these electron spins, you have a diffusion barrier so that the nuclear spin inside won't talk to the nuclear spin outside. But most of the nuclear spin are sitting in a space where the dipolar interaction with the electron is relatively weak, and we call this the bulk nuclear spins. In a typical DNP experiment, the ratio between the volume of bleached or quenched nuclear spins with respect to the total volume is typically on the order of a few percent. It is interesting to note that the highest probability to have a DNP transition is at the diffusion barrier, where the coupling between the electron and the nuclear spin is the highest, but where still spin diffusion between nuclear spin is allowed. So there are two very important questions that I want to ask and try to give a general answer here. Is nuclear spin diffusion efficient? Well, in principle, yes. It can propagate polarization over a scale that is larger than the electron-electron distance within a few seconds, unless your nuclear spins are very diluted. So if your concentration of nuclear spin is on the order of micromolar, you might run into trouble. The second thing is the bleaching important? In principle, no. There are only a few nuclear spins that are bleached, unless your electron concentration would be very high, on the hundreds of millimolar range. So today we talked about the electron spin properties, and we saw that the saturation of the ESR line was involving spectral spin diffusion, also T1 relaxation, and at the end it was a kind of competition between those two effects. We discussed about the nuclear spin properties, and we saw that nuclear spin diffusion was a very important feature that would propagate the polarization across the whole sample in space. And we talked about the interaction between the electron and the nuclear spin. We introduced the concept of a diffusion barrier and of bleaching and quenching. Thank you for following our MOOC on basic steps in magnetic resonance. This was the second part of a chapter dedicated to dynamic nuclear polarization.